This is the MAT125 video lesson number 9 on sequences and series. In this video, we'll look at notation and some examples of sequences and series. A sequence is a function whose domain is the natural numbers, that is, the numbers 1, 2, 3, and on and on. Or the whole numbers is the domain, that's 0, 1, 2, 3, and continuing. Often we use notation like a sub n equals some function of n to explicitly define the nth term of a sequence. For example, you could write a sub n is 1 over n, which would define a sequence that gives you the numbers 1, and then 1/2, and then 1/3, 1/4, and 1/5, and so on. So this is the f of n that I'm referring to in this notation. And this indicates the nth term. So the first term and the third term and so on could be found with this formula. Now sometimes a sequence is more conveniently defined by a recursive definition. A recursive definition must always have two parts. Number one, there's got to be an initial value or seed value, and two, there's got to be a rule defining terms based on previous terms. For example, we could define a recursive sequence, or we could recursively define a sequence as follows. We could say a1, that is the first term, set it to 5, and we could say that the n plus 1 term is 2 times the n term, and that would produce a sequence like this, where you'd start off with 5, and then the next term would be based on the first term, right? The second term based on the first term, so it would be 2 times the previous term, so that's 5 times 2 gives me 10. And the next term is 2 times the previous, and each term is 2 times the previous, and it creates a sequence like that. Okay, my first example to work out here would be this. It says, consider the sequence given by the formula for the nth term a sub n equal 1 over 2 to the power n. What is the limit of the sequence, and how many terms are required before a sub n is less than this 0.000001, which is 1/1,000,000th. Well, here we have a sequence. A sub n is 1 over 2 to the power n, and hopefully you can see that that just goes to 0 as the denominator gets bigger and bigger. We can write that as the limit 1 over 2 to the n is 0 as the n goes to infinity. So you'd say the limit is 0 because this has a determinate form, a form that you can just simply recognize that as the denominator increases and the numerator is constant, the value of this fraction will just get closer and closer to 0. It never will equal 0, but the limit is equal to 0. The value to which it is getting closer and closer is 0, and we can actually make that more precise, and here we can actually connect back to the topic we were looking at with the multiply quantified statements. We could formalize this. We could say that this limit as n goes to infinity of this sequence 1 over 2 to the n is equal to 0. You could say that's because formally for every epsilon bigger than 0 there exists some n element of the, you could say, the natural numbers, or as I wrote it before I used integers. So for every epsilon bigger than 0 there exists some n element of the integers such that if small n is greater than or equal to that big N, then the difference between 1 over 2 to the n and the limit will be smaller than the epsilon. And so here, with epsilon equal to 0.000, I got 5 zeros, 1, 2, 3, 4, 5, and a 1, we're looking for the value of big N so that if you pass that, the difference here is less than epsilon. Ultimately, what we're trying to do is figure out what value of n will make this 1 over 2 to the n less than 0.000001. Now with n going to positive infinity, this quantity is always positive, so I can drop the absolute value here. So I'm trying to figure out for what value of n will this fraction be smaller than that quantity. That's equivalent to figuring out when 2 to the n is more than 1,000,000. So what I'll do is I'll just figure out when 2 to the n equals a million and take a larger value of n. We can solve using the natural log. Take the natural log of both sides. It's about 19.9, so I'll say, you know, let's say choose n equal to 20. I would say after 20 terms, this value of the sequence will be less than that 1 over a million. So we could say for that particular choice of epsilon, we could choose capital N to be 20, so that then for all little n greater than or equal to that value of 20, the 1 over 2 to the n would be less than the epsilon. But 20 is really 20 terms answers the question. Let's move on to the second example. Suppose there are 2 rabbits in an enclosed garden, and suppose after each month the rabbits produce a pair of baby rabbits which after 1 month become adults and also become productive, producing pairs of baby rabbits just like the original pair, all of which similarly continue producing baby rabbits. So the questions A, B, and C are: write a recursive definition for the population of rabbits in the garden, write a sequence for the numbers of pairs of rabbits each month, which is the Fibonacci sequence, and then let's find out how many pairs of rabbits and actually how many rabbits there will be in the garden after 1 year. So this is a famous example attributed to the mathematician Fibonacci that lived around the year, well, it was about the year 1200. Fibonacci lived somewhere around 1200 AD, something about that time frame. He wrote this book that had this example. He was basically introducing the number symbols that we use that are called the Hindu Arabic symbols. He had discovered these symbols written by the Arabs that had been copied from the Hindu mathematicians in India, were brought to North Africa, and Fibonacci, who was from Italy, saw them in North Africa, thought this is a lot better than Roman numerals, and so he took those symbols, wrote a book about how to do math with those Hindu Arabic symbols, brought it back to Italy, and changed Europe. The whole Renaissance was possible then because there was this sort of new technology for understanding things and doing commerce and beginning to do accounting, and mathematics began to improve and science began to improve because there was a technology called the Hindu Arabic numbers that we still use for our number symbols. So this was one of the examples in that book. So to try to understand what's going on, let's start back at the very beginning. I can draw a picture of the development of the population. I'll write B is baby rabbits. Actually, I want to say it's a pair of baby rabbits. I'll use A to represent a pair of adult rabbits. And so the way this is described, what's intended, it's a little confusing when you write it in words, but when you write it mathematically, it's perfectly clear. But we'll start with the wording of the problem, that there was initially 2 baby rabbits in the garden, and 1 month later they are adults. And once they're adults, they start producing babies. And so I'll split off now in the diagram that the adults are still in the garden, but they've now produced a pair of baby rabbits. Those adults that were the original adults, they are still in the garden, and they produce another pair. So this is the months. This is, let's see, in the first month, in the second month, here's the third month, now in the fourth month. What's happened in the third month is that we've got these babies that they become adults. Now, continuing on, in the fifth month, the adults that were adults are still adults. They've produced another pair of baby rabbits. The baby rabbits that had been produced the prior month have become adults. These adults from that month 3, they are still around, but they produce a pair of baby rabbits. So this just keeps going. This is a model of population growth. So in the 6th month, we're going to track this out for a year, and you could do it this way, but there's a pattern that's developing that's important to notice. So let's do one more. Those adults still there, they produce babies. Those babies, they become adults. Those adults, they are still there and they produce babies. These adults are still there, they produce babies, and those babies there from that previous month, they become adults. Now let's count up how many pairs we have. In the first month, there was one pair. Let's list up the pairs. So we had one pair. Here we have still one pair. Now this is two pairs. Then on the fourth month, there are three pairs. On the fifth month, we have 1, 2, 3, 4, 5 pairs. Now those 5 pairs, there's some adults, there's a pair of babies, there's there's a total of 3 pairs of adults and 2 pairs of babies, but overall we have 5 pairs. 1, 2, 3, 4, 5. In the 6th month, how many pairs of rabbits will there be? 1, 2, 3, 4, 5, 6, 7, 8. 8. So can you guess what's going to happen on the 7th month? Well, you can do another row, but there is a very important pattern that's called the Fibonacci sequence that's developing. If you look back at this progression here, this is a sequence of numbers that has a really fascinating pattern. We've got 1 plus 1 gives you 2, and this 1 plus this 2 gives you this 3, and 2 plus 3 is 5, and 3 plus 5 is 8, and actually it will continue with that pattern. The next row would actually have 13 pairs. The next one after that would have 21. So this is called the Fibonacci sequence. I start with 1 and 1 in the way that I'll define it, because what I'll do in this rule, I'm not going to just take the previous and double or add something to the previous. I'm going to use the previous 2 values, and so there actually needs to be 2 seed values, and as I write this Fibonacci sequence in this way, I'm going to start with 1 and 1. Some people go back to values prior, but this is the standard classic version, starting with the pair of baby rabbits. We'll have a 1 and then a 1 given as the seed values. Then you can define all the subsequent terms based on adding the previous 2. So the next one is 1 plus 1 is 2. 2 plus 3, that makes 5. 3 plus 5, that's 8. 5 and 8, that's 13. 8, 13, 21. Add those, you get 34. Add these, you get 55. 89. And when you add 55 and 89, you get 144. And it would continue on with that same pattern. So the recursive definition begins with 2 values, the 1 and the 1. So we could say Fibonacci number 1, Fibonacci sequence term number 1 is 1, and Fibonacci sequence term number 2 is also 1. And then you could say the nth term. Now this is the seed. Both of them together are the seed, and this is the rule. Based on the previous 2 values. So if I say this is the nth value, I need the previous 2 to add together to get the nth term. So all of this together is the recursive definition. So the sequence of numbers of pairs is the Fibonacci sequence that I just put up here. So that is the Fibonacci sequence. So how many pairs of rabbits and then how many actual rabbits will there be in the garden after a year? So actually I stopped on the 12th term. This is the 1st, 2nd, 3rd, 4th, and the 5th month. 6, 7, 8, 9, 10, 11. That's the 12th month right there. So the answer is 144 pairs of rabbits. Which is equal to 288 rabbits. Alright, so let's move on to the last topic for this video. It's actually series, but we're just going to look at finite series and one example of a finite series in particular. So when we talk about series, a series is the summation of the terms of a sequence. And we use sigma notation often to indicate, because you might have many terms, so it's easy to simplify the way that we write it in this kind of form. So for example, if you wanted to add the numbers 1 plus 2 plus 3 all the way up to 100, you could just write it this way. This is This is the formula that I'm using. I'm starting with 1, I'm going to 100, and using this sigma means that I'm going to add each of the values that are given by this formula. Another example, we could add starting with n equals 0. You plug in n equals 0, you get a value, and then you add it to the next value when you plug in 1 and 2 and all the way up to 10, which, by the way, this is actually going to produce 11 terms, whereas this one produced 100 terms. It's 11 terms because we're including 0 in this one. So I'm actually adding the terms of a sequence, and adding the terms of a sequence produces what we call a series. These are examples of finite series. Calc 2 spends a lot of the material, the course, the topic of Calc 2 is analyzing particularly infinite series, and whether they converge to a value or they don't, and all the things that you can do with that. We're just going to look at some finite series. I'm going to look at one particular important example. So a finite geometric is a particular type that has this form where you start at 0 or 1 or really any value, go to some end value that I'm using capital N to indicate. But to be geometric, it has this form where A and R are constant values. A is the initial term and R is the common ratio. And we can find a general formula for the finite geometric series as follows. I'll derive the formula. So, and then in calculus, we can use the result that we're just about to produce to find a formula also for the infinite geometric series. So let me first just develop a formula for the finite geometric series sum. So when we write n equal 1 to big N, A, R, n minus 1, I take the A and the R to be constants here. They don't change in the sum. And you notice that if you plugged in 1, you'll have R to the 0, and that's 1. And so my first term is that value of A. And then I'll add, when you plug in 2, you get R to the 1, so that's A times R. The next term, when you plug in 3, you'll end up with a square. And that'll just continue all the way until when you plug in the last value, which is in big N. So it'll be A, R to the big N minus 1. This is n terms. You can see that it's n terms for one reason, simply because we started at 1 and we went to n. If you look at this, this has a power 1 and 2 all the way up to 1 less than n, but we have this, so it's sort of like a 0 power here, and then 1 all the way up to n minus 1, which means there's n terms total there. So what I'm going to develop here is a formula for this, which we can use to answer my what I'll call this bank problem that figures out the future value, more technically is called an annuity. If we made a bunch of regular payments and we got interest, we're saving money and getting interest, we could find that future value with this, this formula. So I'm going to say A is this result of adding all these numbers, n different numbers. And if you knew what those numbers were, you know, of course, you could just add them all up. But if there's a lot of them, it's maybe inconvenient to add them all up, or to wait for that calculation to be computed. I can come up with another expression for this value in a pretty clever way. So let's do that. It's another formula for this sum. So the trick will be, I will multiply both sides by the value of R. So I'll say, now, you know, this is a number. I don't know what number it is, but this is a finite sum, and so this is adding up to something. So whatever it adds up to is a number, and that number is equal to S. And so I have an equation, and I'm going to multiply both sides of that equation by the same thing, by the number r. If I multiply by r, then I'm going to add a factor of r to every one of these terms. Now the one term right before this would be an n minus 2, and when you multiply by r, you'll get an n minus 1. So I'll say plus a r to the n minus 1 plus a r to the power n. That is the last term when you multiply this last term by another factor of r. Multiplying by another factor of r would just increase this to a power of n. Now the next thing I'll do is just subtract these two values. This one, take away this one. So when I start with the top row on this side and minus this, in other words, I'm taking s minus sr. So if I take this whole entire expression and subtract this whole entire expression, this a doesn't cancel with anybody. So he's still there. But this one, take away this one, these guys cancel, and these guys will cancel. This will cancel with the next term that's in this sequence. These terms will cancel, but this is still there and it's being subtracted. So it's minus ar to the power n, right? All of these terms, we're subtracting these from the top. So this is there, cancel, this one minus this one, they cancel, this one minus this one, they cancel, this one minus this one, they cancel, and then this one doesn't cancel with anything, it's just subtracted. So that's the result there. Now what I'm trying to do is find another formula for s, so I'm going to factor out the s. Say s is s times 1 minus r equals, and here I can factor out a. And if I'm trying to solve for s, we could solve for s by dividing by 1 minus r. Now I was dividing both sides by 1 minus r so that I can solve for s. And so that isolates s, and that gives me this formula for the sum of this finite geometric series with n terms. This is the nth partial sum for a finite geometric series. Or for any geometric series, if you're in the Calc 2 class, I call that a partial sum. So this is the sum of n terms. It's a formula for the sum of a finite geometric series with n terms. And we say a is the first term, and we call r the common ratio. Now let's take a look at an example where we can use this formula. Example 3 says, an investment of $700 is made every month into an account that earns 0.5% interest monthly. 0.5% interest monthly would equate to a 6% annual growth that is compounded monthly. So assume interest is calculated at the start of each month based on the previous month's balance and before each payment is made. So interest is based on previous months and not on the current month's payment. Assume the starting balance is 0. Let b sub n represent the balance after the nth payment. And b sub 0 is 0, so we're starting at a 0 balance. Part A, write the first 5 balances. We'll find a recursive definition for the sequence of balances. In Part B, in Part C, we'll calculate the balance after 10 years. And then in Part D, we'll figure out how many years it takes to reach $1 million with this interest and all of these payments. Now to start off, recognize that if we're going to increase the balance by 0.5% each month, I need to turn that 0.5% into a number without the percent sign so I can do the arithmetic. So 0.5% is 0.005, but then if I want to achieve a 0.5% increase, I'm going to need to have something that's 100%, the original, plus the 0.5%. That would correspond to an increase, a growth of 0.5%. It would have to be 100.5% of what it was before to increase by 0.5%. So you'll see me using this 100% is 1 and 0.5% is 0.005, and so I'll use this 1.005 to affect this 0.5% growth to get a value that is 100.5% of what it was previously. Alright, let's start off by finding the first 5 balances. So we say, okay, the first balance was $700. That's the amount, the first payment. Actually, I guess I need to squeeze in B0 here. So there's B0. B0 was the initial balance, 0, and the first balance after the first payment, that's $700. And then in order to get the balance after the second payment, on the second payment, the $700 goes in, but there is a 0.5% increase on the previous $700 payment, and that's what this is doing. It's increasing the previous month's balance by 0.5%, and then we add in a $700 payment, and so we'll have $1,403.50, right? Two payments of $700 would make $1,400, but where did the $350 come from? It was 0.5% of the $700. After three payments, what we could do is say, well, the payment that we had previously, the $1,403.50, that's the previous balance from the previous two payments, and we'll get a 0.5% increase on that previous balance. So that's going to increase the previous balance by 0.5%, make a $700 payment, and you got $2,110. If you just made three payments of $700, that's $2,100, but this is $2,110.52, and that's of course because of that interest each of those 2 months prior to your third payment. So how about the fourth balance? Fourth balance, we could just take that $2,110.52 as the previous balance in the month before, increase it by 0.5%, and add another $700 payment, and we're looking at $2,821. So we're getting compound interest. We're getting interest on all those previous interest payments, or interest on all the previous interest that had been earned. So that's the first 5 balances, including B0. Part B asked for a recursive definition, and the recursive definition would look like this. Remember, really important that there are 2 parts in any recursive definition. First part being the seed, the initial value. So in this particular example, the initial value was 0. The balance at time 0, or after no payments, it was $0. And then the rule, the second part of the recursive definition, is how you get any subsequent value based on previous values, a previous 1 or 2 or more values. In this case, we only need the previous value. We could say each balance is based on the previous month's balance with an increase of 0.5% plus a $700 payment gives me the next balance. Take the previous month's balance, increase it by 0.5%, add 700, and you have the next month's balance. Question C said, what's the balance after 10 years? Now 10 years is 10 times 12 months. It's 120 months. So I'm going to start to work out like how many terms would we actually need to add together to reach 120 months. So we could do this similar in the way that we just derived the first 5. We could say we knew the first balance was 700. Second balance is the 700 we had initially plus interest on the previous balance, and that was the 1403, and then we could look at the third balance. But what I'm going to do here a little bit differently is to say third balance is $700 payment plus a 0.5% increase on the previous balance. And maybe you can see right here, all of this is B2, the previous balance. So this is the previous month's balance without actually calculating it out. If I leave it in this form, then I can show you how I can develop a geometric series from each month's increasing balance. I'll say take the previous month's balance, increase it by 0.5%, and add the 700, and that's the balance after 3 payments. You can see right here that after distributing this 1.005, multiply it times each of these 2 terms, then I'm going to get this series of 3 terms. B3 is a series of 3 terms. That's a term, 1, 2, 3 terms. And you can see there are 3 payments of $700, 700, 700. There's another payment of 700. There's actually 2 months in which interest was earned, and then the last payment, interest has not yet been earned on that last payment. You can check, multiplying all this out, that it gives me the same 2110 that I had calculated doing the problem the other way. So by the same reasoning, I can continue on now to say the fourth balance after 4 payments. We could say just take the previous balance, B3, but instead of adding it all up and figuring out what it is, I'm going to just leave it in that form and just copy it here. So that was the previous month, and I'm now on the 4th month. I'm going to take the previous balance here, B3, increase it by 0.5%, so I'm multiplying this 1.005 times all 3 of these terms, 1, 2, 3 terms, and when you distribute it, well, when we multiply this 1.005 times each of these 3 terms, we get this expression down here, which would represent the balance after 4 payments. You can see 4 payments, 1, 2, 3, 4. 3 of those payments now have earned interest. You can also think of this as like the payments are being made at the end of the month after interest has already been earned on the balance that was already there. Then the payment is made, and then another month starts, interest is earned, and then another payment is made. So now if we want to extend this to what's the balance after 10 years, let's say that means after 120 months and therefore 120 payments. And if we've made 120 payments, there's actually 119 payments that are earning interest. The payments are coming at the end of the month. And so that last payment hasn't earned interest yet. And the series would look like this. It would be 120 terms, but it would actually end with a power 119, because that's how you create a series there with 120 terms with this particular form. So this is the balance after 120 months, where in the last month no interest is earned. A payment of 700 is made, but no interest has yet been earned on that. So that's where I get the 120 months, because I have 120 payments, and the payments are coming at the end of the month, essentially, after the interest has already been earned on the balance. We could call this the balance after 120 months. This sum is the same sum that I was talking about back when I was developing the formula earlier. When I wrote this formula, I said this S is the sum of the finite geometric series with n terms. And to have n terms, if you started with a term that didn't have the factor r in it, then you'd have to end with an n minus 1 to actually have n terms, right? Because this would be the exponent 1, then exponent 2, exponent 3, all the way up to exponent n minus 1. But then you've got this exponent 0 here on the r that makes it 1 more. So this is n terms, and that's the S that I'm developing a shortcut formula. That's a formula for the S, but that n is the number of terms for a geometric series that has this form, starting with a constant first term that doesn't have that factor of r. So when I get to the question of, okay, so now how much do we have after 120 months? And that's going to be 120 payments. Well, that series is going to look like this, and it's going to go up to 119, but then I do use 120 in this formula. I can say the A is 700, the R is 1.005, the N is the number of payments and the number of months, and that's 120. So I put it into my formula for the sum of a finite geometric series. I use 120, and you can just type it in the calculator as it is here. I would also say that if you're in finance, you'll see it written this way. Both of these factors are negative, and those two negatives cancel, so the answer ends up positive, but it's often written this way as a finance formula. And then when you type that in, you're going to get $114,715.54. You can check this on this website, calculator.net. You can also check this answer in Excel and see that we're getting the same answer. And the thing to keep in mind is that if you have a choice, then what this formula is doing is assuming that payments are coming after the interest is earned in each of those periods, those periodic payments. Interest is earned on the previous balance, and then the payment is made. Or let's say interest is earned on the current balance, and then the payment is made. So let's check the result on this website. I found calculator.net future value calculator. Let's go there. Alright, so this is the website, and I'm going to type in right here the number of periods. Let's make the periods 120 because I want to put the interest rate in months. So if I have 120 months and we start with a zero balance, and if we put a 0.5% interest per period, and the deposits are $700 a month, and let's take payments at the end of each compounding period. So let's see what it comes up with. So that's exactly the same result. So we see the future value of 120 payments in agreement with this formula that is computing the future value of 120 payments of $700 each time, each payment coming at the end of each of the compounding periods. The same result as this website. It's kind of neat to see the interest amount increasing and the principal that's being deposited just going up steadily, but then here the actual balance beginning to really grow faster and faster as that interest adds up. You can also look here and see the same numbers that we were computing for those first four payments. 282107, 282107, the same result. So we can also check this on Excel. Go into Excel and type equals and then FV for future value, parenthesis, type in the rate per period, that's 0.005 because it was 0.5%, and then you can see that it advances to the number of periods. The number of periods was 120. Payments, that was the 700. Let's start with a zero balance, and then you have two options here, 0 or 1. 1 means payments come at the beginning and you get interest for that period, or if you put in 0, payments come after the interest, which is the way that I've been assuming it. It'll give us the same result if you use 0 here. So that's the 114,715 and 54 cents that agrees with the calculation that we got with this formula. Okay, so that's the command in Excel. Let's move on to the last question here. How long until you reach $1 million when making these $700 monthly payments with 6% annual growth compounded each month? Well, we go back to the same formula and find out what N would be with $700 payments. Growth rate of 0.5% a month. We'll find out the number of periods to equal $1 million. So we can solve for N using a log function. We'll use the natural log. So I'll simplify the denominator. Here you could multiply both sides by the negative 0.005 and then divide by the 700, reduce, then subtract the 1 on both sides and get a common denominator. At this point I'll divide both sides by a negative, take the ln of both sides. Once I've got the ln of both sides, I can bring the n down in front by a property of the natural log. And once I have the n as a factor, then I can divide by the natural log of 1.005, use the calculator and get not exactly 420 and not exactly 421. It's just right between, so This is kind of a judgment call. I mean, if you're at 420 months, you're going to be really close to $1 million. And 420 months, you'll be just a little bit over. So I just decided I'll go with 421 because you'll have just over $1 million at that point. Yeah, and we could check exactly how much you would have at 420 months or 421 months with that same website. So let's do that. So 421 months with the same payments, just over $1 million. 420 months, just under $1 million. It's really pretty dramatic to see the interest and the balance just growing there, really way beyond what the total number of deposits accumulate to. Alright, so I think that's the end of the video. I hope it's been helpful.